Welcome to section 3.9. We're going to talk about related rates. Let's start off with an introduction. In a related rates problem, we're asked to find the rate of change of one variable or quantity in terms of the rate of change of another variable or quantity, which is usually more easily computed. So suppose that x is a function of t. And we have x of t. And we know the information about the rate of change of x with respect to time t. So we know dx dt. However, we are asked to find the rate of change of y with respect to time t. In other words, we're asked to find dy dt. Then we need to find an equation that relates the two quantities of x and y. Say we're dealing with a circular situation. Then let's go ahead and take the derivatives of both sides. I would have 2x, and then because I'm taking the derivative with respect to t, I would have dx dt. Remember, before we were just letting those x's fly. Now everything's with respect to t. For the next one, for my y squared, I'll bring the 2 down. I'll have the y, and then I have dy dt. And then I take the derivative of 25, and I get 0. So by the chain rule and implicit differentiation, we end up with this equation for the change of y with respect to time. Okay. That's essentially what we end up doing for related rates. Now, this is just some rando introduction. So let's look at what we would do for other types of problems. Let's look at the procedure for solving related rates problems. First of all, draw a good picture. In fact, draw hundreds of pictures. So I'm not going to get rid of that draw good pictures. Hundreds of them. Draw good pictures of the problem situation. If possible, assign variables to the quantities that vary. Now, some things I would do. Include your moving parts. Draw your pictures from many perspectives. And draw it in many different sizes. Basically, the more you can draw your situation, the easier it will be for you to start applying calculus to the situation. All right, once you have a picture, you should be able to find a relationship or an equation that relates the variables. Right? If it's a circle, maybe you'd look at the equation of a circle or the equation for the area of a circle. What if it's a triangle? You could have the formula for the area of a triangle or Pythagorean theorem, maybe the law of sines. It just depends on what you have in the picture. Next, we're going to differentiate both sides. And you're going to use the chain rule to differentiate both sides with respect to time t. You're then going to substitute your known / given values into the resulting equation and solve for your unknown rate. All right, so draw a picture. Use the picture to find a relationship or an equation. Then use the chain rule and differentiate both sides with respect to time. So like if I have an area equation, let's just say I have like area equals pi r squared. I'm going to take the derivative with respect to t of both sides. And what I'm going to end up with is dA dt over on the left side. On the right side, this 2 will come down, and I'll end up with 2 pi r. And then because I took the derivative of r with respect to t, I need to use dr dt. And then I just plug and chug. And solve for one of your rates, right? We either solve for this rate here. This is the, you can't see this. You know, I solve for this rate here. This is the change of radius with respect to time. If I had a circle, I would be looking at that rate. That would be dr dt. Or I'd be looking at this rate. This would be the change in area with respect to time. Just depends on what we're working with. Let's look at a specific example. When a rock is thrown into a pond, it creates a circular ripple, the radius of which is increasing at the rate of 3 feet per second. At what rate is the area of the ripple increasing when the radius is 15 feet? Okay, so first thing I would recommend is draw a picture. So here you've got a stone that's thrown in, and here's your radius. And as time goes on, your radius is getting larger because the circle is getting larger. Let's look at what they're giving us. So the given rate in this case is the radius. They're saying that the radius is increasing at a rate of 3 feet per second. So the change of my radius with respect to time is 3 feet per second. And they want to know what's the rate of the area of the ripple increasing when the radius is 15 feet. So what I don't know is the change in my area with respect to time. And that's area, so that's going to be like a feet square per second type of unit. Now I also want to point out, we know that the radius is 15 feet, but keep in mind that the radius is growing. So this is just a moment in time that we're looking at. So r is not fixed. R at this moment in time is 15 feet, but we know that the radius is growing by 3 feet per second. All right, so we're looking for the rate of change of the area. So let's look at the area function. We know that the area of the circle is going to be pi r squared. We know that r is my radius of my ripple, okay? And this is growing. So this is growing. And this r, this is my r. It's my radius, right? It's the radius of my ripple. This is also growing. Well, number 2 is going to be easy for us, finding a formula that relates area and radius. Well, we know that the formula for the area of a circle is pi r squared. Next, we're going to take the derivative of both sides. So I did this on the previous slide. But let's rewrite it for fun times. On the left side here, I'm just going to get dA dt because the area of that circle is growing, so there is a rate. Over here on my right-hand side, this 2 is going to come down in front. So I'm going to have 2. Pi goes along for the ride. The r goes down to a power of 1. And then I need to remember that the radius is not still. It is growing as time is going on. So there is a change of radius with respect to time. Now I'm going to do my step 4. My step 4 is my plug and chug step. So I'm going to plug in the things that I know into this formula. I don't know the change in area. That's what I'm trying to find. At the moment that we're trying to find the area changing, we know that the radius is 15 feet. So I'm going to put that in for r. And the radius is changing at 3 feet per second. So I'm going to put that in for dr dt. Once I have everything plugged in, I can go ahead and solve for the change of area with respect to time. I'm going to end up with 2 times 15 times 30, which is going to give me, it's not going to give me that. It's going to give me 90 pi feet squared per second. And notice, that's a positive rate, right? That's a positive rate, which makes sense because the ripple is growing as time goes on. All right, good job. All right, let's look at the next example. I've got a person who is 6 feet tall, and they are walking away from a street light. So here I got a street light. And it looks like the sun on a stick. Sorry, terrible street light. I've got a 6 foot tall person who's walking away from a street light that is 20 feet high. So the street light is 20 feet and the person is 6 feet. We assume that they're both perpendicular to the ground. And this person is walking away. They're walking away from the street light at a rate of 2 feet per second. So let's split this little triangle up. From here to here is x. Let's call from here to here y. And we know that the person is walking away. So dx dt is my 2 feet per second. Then they want to know at what rate is the length of the person's shadow increasing. All right. So in other words, we're trying to find the length of the shadow. All right, now this is kind of a physics thing, but basically what we're trying to find is not dy dt. We're not finding dy dt. We're finding dx plus y dt. All right, so my given rate is my dx dt, and he's getting farther away, so it's growing, so it's a positive 2 feet per second. And what is unknown is the change of the x plus y with respect to time. So I'm going to let x be the distance from your street light to the person. And I'm going to let the y be the distance from the person to the tip of the shadow. Now, let's find an equation that relates x and y. Well, I don't know about you, but to me, this is a nested triangle situation. So essentially, I can take this big triangle here, and if I look at that, I'm just going to draw it in a smaller form. Here I've got x plus y and 20. And then nested in that big triangle is a smaller triangle. Here I've got this, I'm going to draw it so you can see it a little bit easier, but I've got the smaller triangle here. And the smaller triangle is just y and 6 feet. Now, nested triangles are similar figures. They have parallel sides. You can use proportional reasoning. So what I'm going to do is I'm going to set up a proportion, and the proportion I'm going to set up is going to be this one. There are multiple proportions that you can set up, but understand that as long as you get the same answer, you've set up a correct one. Just make sure you're using corresponding sides. What I did for this one is I said, okay, 6 is to y, as 20 is to x plus y. So, similar figures. All right, but I don't want to take the derivative of this right now. Yuck, I'd have to use some power rules and stuff, and forget that business. So what I'm going to do is I'm going to use proportional reasoning, and I'm going to find their cross products. So I'm going to multiply these two. And then I end up with 6x plus 6y equals 20y. So then I end up with 14y equals 6x. And then that means that y equals 3/7 x. So if I plug that y equals 3/7 x back into my length that I'm trying to find the derivative of, then I'm really saying that x plus y is the same as x plus 3/7x. All right, so I didn't use Pythagorean theorem. I didn't use an area formula. I used corresponding sides and proportional reasoning. All right, but now I need to take the derivative with respect to time of both sides. So over here, I'm just going to get that derivative of x plus y with respect to time, which is what I'm looking for. Here, I'm going to actually take the derivative of the individual pieces. Now notice, x plus 3/7 x, I could have added that together first, right? So I would have gotten 10/7 x. But even if I don't, if I just take the derivative of them individually, I'm going to end up with dx dt plus, now remember this is a power of 1, multiplies down by the 3/7, so I get 3/7 dx dt, which would give me 10/7 dx dt. So now I'm in my fourth step, my plug and chug step. Okay, and I'm just going to rewrite what I have so we can kind of plug it in there. All right, this value here, we don't know what that is. That's what we're trying to solve for. 10/7 is just going to go along for the ride, And then dx dt, that was given to us. That's how far or how quickly the person is walking away from the street light, which is 2 feet per second. So when I plug that in, I get 20/7. And this is feet per second. This is the change of this whole length right here with respect to time. Next example, a 4-meter ladder is leaning up against a vertical wall. If the bottom of the ladder is pulled away from the wall at a rate of 1 meter per second, what is the rate at the top of the ladder moving down the wall when the top is 2 meters from the ground? All right, so we got a 4-meter ladder. That's this piece right here. This is 4 meters, and I want to say that keep in mind that this is a fixed value. Like the ladder's not shrinking or changing as it goes down the wall. Now let's say that the ladder is X feet away, the bottom of the ladder is X feet away from the wall. And they say that it's being pulled, okay? It's being pulled away from the wall at a rate of 1 meter per second. So that means that this is changing here, and dx dt is 1 meter per second. They want to know what's the rate at the top of the ladder moving down the wall. So what's this? Well, let's call this length y. And that's this length here to here. And then this change as the ladder slides down is going to be dy dt. And that's what we don't know. Now I'm going to point out a couple of other things. This is growing. My dx dt is growing. It's getting farther, right? The ladder's getting farther away. But my y is not growing, it's shrinking. The closer that ladder gets to the ground, the smaller that y value is going to be. All right, so we already wrote it in the picture, just for clarification's sakes. My given rate is my 1 meter per second of my of my x. What I'm trying to find is how quickly is the top moving down the wall. Now, they want to know a specific time. So they want to know when the top is 2 meters. So we don't know what x is, but we know that y is 2 meters. We can actually figure that out. At this picture in time, I've got 4 meters. X is an unknown, and they're looking for when y is 2. So I can use Pythagorean theorem to figure out what x is at this moment in time. And I always think of this is like a snapshot in time, okay? Because if I took a picture at any other time, these values would be different because the ladder's going down and it's sliding out. But at this moment in time, I can use Pythagorean theorem and say, okay, 4 squared, which is 16, take away from 2 squared, which is 4. So 16 minus 4 is going to give me 12. And x at this particular moment in time is going to be the square root of 12. Let's see if we have to use that. The square root of 12, by the way, is 2 square roots of 3. All right, so x is labeled on my picture, but it's basically the distance from the bottom of the ladder to the wall, and y is the distance from the top of the ladder to the floor. All right, well, if I were to look at this right now, the easiest formula for me to use, honestly, especially because I'm using dx dt and dy dt, is the Pythagorean theorem. So I am going to use the Pythagorean theorem. And right now I know that x squared plus y squared equals 16. So in this next step, what I'm going to do is I'm going to take the derivative with respect to t of both sides of this equation. And remember what we learned in our implicit differentiation section. In fact, this is why we learn implicit differentiation, or one of the many reasons why. So we're going to take the derivative of each piece. So the power of 2 is going to come down. I'm going to end up with 2x. And then because I'm taking the derivative of x with respect to time, I'm going to write dx dt. Next, I take the derivative of my y. My 2 is going to come down. I'm going to have 2y. And then the derivative of y with respect to time. And then over here, my 16, if I take the derivative of 16, that's going to give me 0. All right. I took the derivative. Let's go ahead and plug and chug. All right, let's go ahead and plug and chug. So let's plug in what I know. The 2, that's going to go along for the ride. The x, I just found that. Okay. The x is going to be 2 square roots of 3. And dx dt, they gave that to us as well. That's 1. Next, I'm going to plug in my values for y. So I've got the 2 here. They told me the top is 2 meters from the ground. So I'm going to have 2 meters here. And then dy dt, that's what I don't know. That's what I don't know. And then my 0 just goes along for the ride. All right, well, this is a great situation. I'm just going to simplify. And see that this is perfectly set up for me to solve for dy dt. So first I'm going to subtract the 4 square roots of 3 from both sides. Next, I'm going to divide by 4. And I end up with negative square root of 3. That's my dy dt. So this rate right here is negative square roots of 3 feet per second. I'm sorry, meters per second. Now, does that make sense? That answer there? Maybe not the numerical, because I think sometimes it's hard for us to visualize the numerical aspect of this. But it should make sense that it's negative, right? Because remember, that ladder is sliding down the wall. So y is shrinking. So when you do your work, you better get a negative answer. All right, let's take a look at this next one now. These are a really complicated problem, so I'm going to have to do it over a couple of slides so I can fit it all in. Using a conical tank, okay, keep in mind the way that cones work is that we've got some interesting relationships between the radius and the height, and we are going to use that. So here we've got some spigot, and water is flowing into the tank at a rate of 3 cubic feet per minute. So we know that the dV with respect to time is 3 cubic feet per minute. The tank has a radius of 2 feet at the top. Okay, so the radius here is 2 feet at the top. And it has a depth of 4 feet. So this whole length from here to here, this is 4 feet. They want us to know how fast is the water level rising. So just imagine like here we're filling in the water's this high. How fast is the water level rising? I'm going to draw this in a different color. When the water is 1 foot deep, 2 foot deep, and 3 foot deep. All right, now H is my height. So understand I'm going to set up this problem and then I'm going to do 3 different plug and chugs. I'm going to look at when the height is 1 foot, 2 foot, and 3 feet. All right, this little piece right here, the green, that's my height. That's changing. When I'm pouring water into it, right, my dH dt is this change as the height is getting larger and larger. And I don't know how fast the water level is rising. So that's a question mark. Here's my R. Notice as I get taller and taller with the water that my radius will get bigger, right? So if I were to just draw this kind of in a 2-dimensional respect, we can see here's my H, here's my R as the water goes up and up. Now R, notice, R is getting larger and larger. So I may need to worry about the dr dt, but let's find out for a second. All right, I'm going to plug some things in. I'm also going to take a look at the slice here of the cone. Think if this is H and if this is R, and then the full length here, the full length for this thing, that's not the H. That's going to be 4 feet. And then this full length here, that's not R. That's going to be the 2 feet. So I'm going to write this H over here so we don't have any confusion. All right, let's fill in the stuff that we know. We know our change in volume. We also know that it's positive because I'm pouring water in, so the volume's getting bigger and bigger. It's growing. What we don't know is dH dt. And notice, no one said anything about the change of the radius with respect to time. So what we really have to think to ourselves is it not needed? And it's not that it's not needed, but it does need to be substituted out. So we need to substitute out. All right, so V is going to be your volume of water in your tank at whatever time t. H is going to be the height of your water in the tank at whatever time t. And then R is your radius of your water in the tank at whatever time t. And all of these are growing, right? All of these are growing. So all of these rates are going to be positive when I look at their rates. So let's find an equation that relates V and H. Well, oops, what did I just do? All right, so first thing, it's a cone. So I'm going to use the formula for the volume of a cone. All right, so I've got 1/3 pi r squared h. Now, I'm going to tell you something. We don't want to take the derivative here because I have, now pi is just a number, 1/3 is just a number, but I've got volume and I've talked about height, but I don't want multiple variables here because I wasn't given a rate of change for the radius. So I need to get rid of the r. So what I'm going to do is I'm going to look at the triangle. What would not be ick, aka good, would be if I get a formula for the volume that is just in height only. So let's work on that. Let's take a look at this guy right here. If I use the nested triangles, I have 2/4 equals r over h. Which means if I solve this for r, right, multiply both sides by h, reduce it, r is always half of h. Well, that's doable. So if I say that volume, and I'm going to write it as pi over 3, volume is pi over 3 r squared h. And then if instead of r squared, I put in h over 2, then I can say volume is pi over 3 times h cubed over 4. And then let's simplify and put that back into this one. What I end up getting, I'm going to, oops, it's not an eraser. What I end up getting for my function I can take a derivative of is going to be pi over 12 times h cubed. This is the one I'm going to take the derivative of. All right, so again, remember, I'm relating v and h. No derivative rate for the radius was given. So it's not that it's not needed, but it definitely wasn't given. So I have to substitute it out. And I use this relationship of triangles to do that. And that gave me this volume formula for a cone that's just dependent on height. And that bad boy, I could take the derivative of. Okay? So let's just remind ourselves we've got V lies. I'm trying to write stuff. V equals pi over 12 h cubed. All right, so we're in my derivative stage. So I'm going to take the derivative with respect to time of both sides. All right, so on my left side, I'm just going to get the dv dt. On my right side, the 3 is going to multiply by the pi over 12. The 3 and the 12 will cancel. So what I'm really going to end up with is pi over 4, but I'll write out the middle steps in the meantime. And then the h goes along for the ride, and then the power of h reduces to 2. And then I got to remember, I'm taking the derivative of h with respect to time. So I need to squeeze in that dh dt. And then let's simplify. I've got the rate of volume changing with respect to time. Let's reduce this. I'm going to have pi over 4 times h squared times dh dt. And now I could do my plug and chug step. This is the home stretch step. Plug and chug. All right, so remember, I've got an ABC here. They want to know how fast is the water level rising when the height is 1 foot deep, 2 foot deep, and 3 foot deep. So I'm going to use this function here. I'm going to plug and chug and then solve it for dh dt. So for A, my dv dt is, remember, 3 cubic feet per minute. Why are you not writing? All right, my dv dt is 3 cubic feet per minute. So I plug in here. I'm going to get 3 feet per minute. Pi over 4 goes along for the ride. H squared is going to be 1 squared, because for A, I'm using h equal to 1, and then dh dt. All right, in order to solve for this, because I end up with 3 equals pi over 4 dh dt, in order to solve for this, I need to divide both sides by pi over 4, or multiply by the reciprocal. So then I would end up with 12 over pi. And this is a height measurement, so it's just going to be regular feet, linear feet. And this is in feet per minute. For B, and I'm still in the plug and chug stage, I'm going to do the exact same thing. For my dv dt, I'm going to put in 3. I've got pi over 4, and then h squared. In this case, h squared, h is 2, so I'm going to have 2 squared, and then I need to solve that for dh dt. My 2 squared and my 4 cancel, so I'm just left with 3 equals pi dh dt. And then if I want to solve this for dh dt, I'm just going to divide both sides by pi. I'm going to end up with 3 divided by pi feet per minute. For the last one, I've got h is equal to 3 feet. So again, I'm going to take my derivative function. My change of volume with respect to time is 3. Pi over 4 goes along for the ride. H squared in this case is going to be 3 squared. And dh dt is what I'm solving for. I end up with 3 equals 9 pi over 4 times dh dt. If I want to solve this for dh dt, I need to divide by 9 pi over 4, or divide by the reciprocal, or sorry, multiply by the reciprocal. Either way, I'm going to get 3 times 4, so it'll give me 12 over 9 pi, but I can reduce that. So get rid of those factors of 3, and I'm going to have 4 over 3 pi feet per minute. And this is my dH dt when the height is equal to 3 feet. All right. So here's my answer. When the height is 1 foot, the water is rising at 12 divided by pi feet per minute. When the height is 2 feet, the height is increasing at 3 over pi feet per minute. When the height is 3 feet, the height is increasing at 4 divided by 3 pi feet per minute. All right. I know these are tough, but I have faith in you. Good luck.